right. It seems I can get started. Right. Good morning, everyone. Welcome to the business track of the OpenSUSE conference. Today I have now 25 minutes to talk about ARM, everything you want to know. So, first of all, why OpenSUSE for another architecture? I mean, OpenSUSE already runs on your laptop, your server, your desktop. Is there anything more? Of course, SUSE also runs on many other cool machines. So like this one, this is a high-performance cluster with 150,000 cores, x86, pretty decent amount of memory. You also have SUSE running on the Watson machine that won Jeopardy some time ago, running on PowerPC. SUSE is, of course, also on mainframe. But my question would be, what about OpenSUSE on something completely different? Like, for example, this little device. You can see it's a very small black box. It has all the inputs and outputs that you're used to. So it has Ethernet, it has HDMI, USB, SATA output. So it's a pretty decent device. It has an ARM core inside. It has roughly 1 GB of RAM, so you can do a little bit of stuff with it. It's quite kind of neat. There's similar kind of devices. This one, so it's a development board, basically QB board, similar performance, similar memory. This is a similar device. But recently, also there seems to be some movement in the market regarding ARM on server architectures or server form factors. And that looks quite interesting. So for example, there are two machines here, one from HP, one from Dell, that provide you basically with a cluster of many ARM machines in a very small form factor, combined with normal hard drives, with lots of RAM. Yeah. Seems to be pretty interesting. Okay, so how did we start with OpenSUSE and ARM? First of all, what is ARM? ARM is to be the most popular CPU architecture, so that's one thing that I found quite interesting. There were more than 25 billion CPUs sold, which are ARM-based. Of course, most of them end up in smartphones or in little small network devices, so you don't actually see it. But it's still a very impressive number, I think. Their slogan is low power leadership. So this pretty gives you the impression what they're heading for. The architectures are optimized for system on a chip, which means you have only one silicon which contains all the I/O stuff, everything you need to run a full computer. They offer various designs. The most interesting ones for OpenSUSE are basically the classic ARM processor designs. That's ARM version 5 or ARM version 6, like the Raspberry Pi, for example. It is very low power, very low performance, and it often doesn't have any hardware floating point support, so you kind of have some hurdles to take. But there's also a different series. It's called the application processors, usually Cortex A something, and they have usually a vector floating point unit. They have SEMD instructions. They have support for up to 1 terabyte of memory, which is quite decent. And some of the variants have also virtualization support. So first I want to go a bit about the pros and cons. So the overall marketing factor basically of ARM is that it provides a very good performance per joule ratio. So that means it doesn't use a lot of power for what it can do. The absolute high numbers of the performance is not extremely high. So if you're looking for the fastest architecture, then ARM is probably at the moment not the way to go. It seems to have overall still quite a decent advantage over other architectures when it comes to actually power consumption. If you're thinking about a workload that is not primarily CPU bound, so anything with network I/O, some crawling, indexing, whatever, that can scale out, maybe web load or something like that, then it seems to be quite interesting because the power consumption overall seems to be quite low. So how did we build OpenSUSE for ARM? So first of all, we are using the build service, which is kind of neat tool. So just to give you an impression, It offers a very systematic approach for rebuilding a distribution. It tracks all dependencies between the packages, and it has image and installation media building integrated. So one thing we are really focusing on is to have a reproducible build. So that means if we are doing only one change to the system, then we can be pretty sure that the created resulted image only has this one change included. So that we don't need to retest everything from scratch. We are pretty sure that the build has been reproducible and it contains only the changes we want. So I'm going a bit more into the technical sides on how we build a package on x86. So for security reasons and for being able to have a reproducible build, we build every package in a locked-down sandbox. So the sandbox has no network access. It has no access to physical hardware, so the build process cannot actually detect anything of the build machine. Of course, we don't want that because we are not actually running this distribution on the system where we are building. And everything is run with minimal privileges only to ensure that if there's any malicious behavior in the build process, it doesn't harm the build system. So you can see we have basically a stack of the physical hardware with a normal x86 machine kernel base system, which is just good enough to run KVM-Xen. And within KVM-Xen, we are setting up again a minimal system where we are actually building the package. And on the normal architectures that OpenSUSE supports, basically x86 and now PowerPC, we use, as I said, KVM-Xen. On ARM, however, when we started the port, there was no virtualization support whatsoever. So meanwhile, there has been some experimental port of Xen announced for ARM, and I think even KVM has a prototype running, but it was not available at the time we started. And in addition to that, the hardware we had didn't actually have any support for virtualization. So we were kind of stuck, and we thought about how to get out of it. And one idea we had is basically use QEMU. So QEMU is both a system emulator and a CPU emulator, and we're using it in CPU emulation mode. So we can actually run ARM binaries on normal x86 hardware using the emulation. So this is the setup how it looked initially. As you can see, we're still building in the sandbox, and we are still running the normal Linux kernel. However, between the ARM build system and the kernel, we have added CPU emulation. The problem with this approach is that the problem with that is that we need to actually make the emulation good enough to be able to build all the packages. And as we learned during porting, there are quite a lot of interfaces between the kernel and user space. So for example, of course, we needed to emulate all the syscalls, all the I/O controls. One thing we learned is that we also need to emulate certain files in /proc. So in /proc CPU info, you can usually see that some information about the processor that the machine is running on, and certain ARM binaries we're expecting to find in proc CPU info some information about the ARM processor. But in our emulation, initially we only had information about the host architecture there, so the binaries usually crashed because they weren't dealing with having a CPU that is called x86-64. That was kind of interesting. Another problem that we have is that there's a special communication path between the kernel and user space. It's called netlink, which can be used to query interfaces on the system. This we just blocked so far because we don't actually want the build to know anything about network interfaces. We can't do anything with it anyway. So that's so far good enough. And one thing we learned is that test suites are really mandatory. So for every package that we build, we really try to compare the test results that are being run after the build is finished within the emulated environment and within the native environment. And if they match match up, then we can be pretty sure that the emulation and the emulated build worked quite well. And one thing that we often get asked is why we are not using cross-compiling, since everyone else in the embedded world especially seems to be doing that. The main reason for that is that we are trying to build the whole distribution, and many of the packages are not really prepared for cross-compiling. So you can get pretty far with the base system and embedded environments, but you can't easily build other packages with it. So for example, many packages use some kind of code generating tool during the build, which you wouldn't be able to run in a cross-build environment. So just to give you an impression on how far or how fast the setup would be, we initially benchmarked basically an OpenSUSE 12.2 rebuild. It's kind of adding up all the rebuild times for every package. So this is not the actual time, but it's the time it would take if we would have only one machine for building the distribution. So you can see in the red bar, it would almost take 3 to 4 months to build the complete distribution. So that seems to be quite slow. If you compare it to native hardware, so the Cortex A9 1 GHz machines, even these little small devices, it seems to be building quite a bit faster. So this doesn't seem to be a very good approach. So we thought again, there can be some things that we could be speeding up. So one part where we're losing quite a bit of time during build is actually unpacking the sources and doing various configured stuff and preparational steps. Many of the binaries that are run during the build are actually not really architecture specific, and we can just replace them in our setup with a native x86 package. So for example, the first step that is usually done is untowing the tarballs with the sources and then decompressing the sources. And we can run xz as an x86 64 binary, which is running on our hardware a lot faster than an emulated ARM binary would run. And this way we can gain a pretty decent speed up. Of course, if we're spending a bit more time on it, and that's what we actually did, is we also replaced the compiler, the linker, and even our PM build itself with a binary that is located in the normal paths, but is actually producing cross-code. So we are kind of doing a cross-build that looks like a native build. So all the configure checks and everything detected as a native build, and they run in the native build code path, which is what we want, because then it does actually the configure checks, it runs the test suites and everything that we are used to from other architectures. And we can, however, still make use of the speed up with using the cross compiler instead of an emulated compiler. So here's the current rebuild time compared to the one before. We basically doubled the speed. So this is not quite what we expected. We actually expected a bit of a faster result. The main problem seems to be that we have more than 80% of packages that are relatively small. So all the speedups that we did were heading towards really big packages, like lots of compiler invocations, lots of untowing, and so on, lots of CPU. But it seems most of the packages are actually small packages that just do a little bit of things and then run tests. And all the tests are run in emulation, and yeah, that's where we lose quite some time. So the usual question is, does it build? Yeah, it does build. Does it actually run? So what do you think? Hands up for who thinks that it runs.
Somehow.
Okay, so yesterday there were many more people. Either they told you. Okay, so it didn't run yet. Do you have any idea why? So we actually forgot some pieces. So one piece is we need to actually have an ARM kernel. So far we built all the packages of the complete distribution without ever building any kernel. because we had no use for it. We were using the x86 kernel in our sandbox. We used ARM CPU emulation. We didn't have any kernel, so we weren't able to run it. So let's go into the details about the kernel. Unfortunately, on ARM, the situation is not as easy as it is on other architectures. So the main difference is that you have many different kernel flavors, and basically one for each SOC generation or SOC specific type. And it has a lot of code duplication and lots of incompatible variants, so you need to really configure for which particular device you want to build a kernel for. In addition to that, ARM usually doesn't have anything like a BIOS or anything which does the early hardware initialization. So what we need to do is to actually boot with a special bootloader, so for example U-boot, that initializes the hardware good enough so that we can actually load and run the kernel. And then also the kernel needs to do the proper hardware initialization in order to be able to boot up the system completely. And currently, in the upstream kernel, there are more than 50 variations. Of course, except for the upstream kernel, there's also a downstream kernel. There are many other kernels that you need to pull together, so not every support for every device is upstream. That seems to be still kind of a mess. And every small variation of a SOC requires a custom kernel. It usually also requires a custom U-boot. And yeah, so either we embrace it, that's what we currently do, or we settle on one of the SOC generations that can be handled with a more uniform image. So recently, especially for the ARM server market, it seems to be that everyone is focusing on this single C image kernel support, which means that you actually have just one kernel that can abstract away all the specifics of the particular SOC that is being used in the machine and can do the hardware installation in a generic enough way in order to be able to use only one kernel for a wide variety of systems. Okay, so we kind of sorted out the kernel problem. The second part is we actually need a deployment method. The first challenge we have is usually we build CDs, but we don't have a CD drive for ARM devices, at least usually we don't have, and it doesn't really fit. And the second problem is due to the different kernel flavors and the different bootloader that we need, we are not actually able to build a single media. So the single install media, the DVD you put in order to install your laptop and configure the software and so on, that's not really possible because in order to boot up the system, we already need a specific bootloader and a specific kernel so that we can actually do anything like installing. So instead of that, we came up with a different build target for ARM, and we implemented that in Kiwi with the help of Marco Schäfer. Basically, he did all the work. So first of all, we created a generic root address target or change root target. That's basically just a tarball with OpenSUSE root files, the minimal root file system. This is quite useful if you have already a device that runs a particular Linux flavor. In some cases, even Android works pretty well. And you have root access there, so you can just untar the file and change root into it. And then you have already an OpenSUSE system that gets you started. For the full support, we also provide U-boot-based images that you can DD on a SD card and put in your device, and then it should boot up just fine. Okay, so just to answer the question from before, does it run? Yes, it does run. I'm just going over the list of test hardware that we currently have, as I'm a bit running out of time. I'm skipping over that. So one thing I want to mention is that we are working on various devices, and of course you can contribute. This is an OpenSUSE project. Everything is done in the public instance of the build service. You can test the latest images that we provide there. You can maybe give us hints on which test hardware that we should look at and try to enable it, or you can do the fun and do the enabling yourself. And you can help us with the missing pieces there. So this is just a snapshot of the build service. You can see that we have various sub-projects for OpenSUSE 12.2. So there are already several community members working on packaging up all the missing pieces for a particular device so that you can build, together with the ARM distribution that we created, a fully working system for this particular chipset. All right. So basically the status is that we are pretty well prepared for any future device that might come. We have basically developed an acceleration layer based on QML that can be reused for anything. So it could be reused also to build OpenSUSE for other architectures as long as QML supports it. It can be used without any native hardware. I mean, that's what we also did. Two new devices that I saw just recently in the press is basically the new Chromebook. It's nowadays based on Cortex A15, which is a pretty decent CPU. Unfortunately, it's completely locked down, so Chrome OS uses some kind of secure boot system. We don't actually know how to hack this device, so we already pre-ordered it. When it arrives, we will try to figure it out. A similar thing, which is maybe even worse, is the Windows AT based Surface computers. So those are touch tablets that have also an attachable keyboard. Of course, there we also don't know it has a lockdown. So we are sure that it has a lockdown booting method. So it seems to be a challenge to get OpenSUSE on it. And we don't actually know how much the device would support Linux at all. Okay, so we have some tablets already where we are working on getting some OpenSUSE on it. This is work in progress. One thing I wanted to mention is that there's basically a new architecture coming up. It's called ARM version 8. It's basically the 64-bit ARM, if you want to put it very simple. It has full backward compatibility with ARM version 7, which is what we are currently using. It has some enhanced instruction sets. It provides full 64-bit support, so you have all the advantages there. Unfortunately, it's not really publicly available yet, but it's supposedly coming out very soon. Yeah. All right. Almost running out of time, but are there any questions? Oliver? You mean X-Windows system? Yes, of course. So it depends a bit on the machine type. Many of the machines we only run with frame buffer because we haven't actually spent the time on getting all the 3D acceleration supported for this particular type. In some cases, you would really need to use a very specific kernel that has the device support inside. Currently, we are trying to focus on just using the upstream kernel as good as it gets, so we don't want to enable all the particular devices on our own. But if there's someone interested in doing that, then of course I think we can always create a contrib project that contains the particular device with the necessary support for it. So in general, most of the devices I have one with me are running in frame buffer just fine. Of course, you're losing quite a bit of performance with that compared to an accelerated device. All right. Any other questions? Robert?
So how hard is it to pick any Android tablet and make it an OpenSUSE? I mean, the kernel obviously already runs there, right? So it's a user space question more.
Right. It really depends. So we've had pretty good successes with some tablets. So really, so the first thing you have to do is basically to get the bootloader to load something else. Once you get to that, you need to provide or build a kernel that works for this particular device. And once you have those two steps mastered, everything else is just 5 minutes of work. So you combine your way of booting your kernel together with the standard OpenSUSE distribution, and you have a working image. For some of the devices, this is pretty easy because they have a really open bootloader. And you can just say, instead of booting from the internal SD card, boot from my device that I just plugged in or something like that. And you're pretty much set within 5 minutes. There are other devices where it's not that easy. So it really depends on, so most of the consumer devices are completely locked down, and you first need some kind of trick to open up the bootloader. Otherwise you're pretty much stuck. So that's why we are focusing on this more kind of development hardware, because they are really open and it helps us to actually find the problems with the distribution and have a very solid base that others can build the systems on.
Regarding the kernel, there are lots of devices out there where you probably will never be able to run a real upstream kernel on, but you get some vendor kernel and that's it. Are there some preparations to be able to basically, okay, I install a kernel from a vendor, but the rest I can use OpenSUSE?
Absolutely.
Basically not depending, for example, on the newest features of kernel 3.0 because, or 3.5,
right.
6, 7, because sometimes all you get is 2.6.26 or something like that.
Right. So the basic setup that we have is that we have the standard repo that's called osc12 ARM. This contains just the standard OpenSUSE kernel, so basically the upstream kernel with some additional patches, just a few of them. Everything that can be enabled with that device, you can use those images. For everything else where you need a specific kernel, we are creating those contrib projects. So for example, in contrib origin, there's a very specific kernel inside that's the only one that we found that to be working on this particular device. Unfortunately, there are some problems when you try to boot an OpenSUSE up with a very old kernel, for example 2.6 something or so, because I recently learned that systemd has a dependency on quite a recent kernel, and OpenSUSE is overall switching to systemd, already started to switch basically. Yeah. So at the moment there's no real solution. Maybe some of the missing pieces can be easily backported. I don't really know for sure. Right.
So thank you for your questions. We need to prepare for another speech, which will be about the standard. Thank you.
Okay, thanks a lot.